Hello class, this is CSE-4600, section 62. This is the video regarding your lab, so this is a little bit of lab instruction. This is a bit of guidance for your lab. Remember, your lab consists of two parts. The first part is you're going to write a hello world program that uses the fork and wait system calls, and then you're going to make another one that uses pthread calls as part of the hello world program. So you're making two hello world programs, and then you're going to modify them so that they print out different outputs. So before we do anything related to multi-threading or multi-process, whatever, of course we got to start with the introductory hello world program and then build up from there. So really this is just a head start, and if you're gonna be taking, say, CSE-5250 in the future, I taught CSE-5250 in the past, you might still be watching my videos as part of CSE-5250, whoever's teaching it right now. The point is this. This is just the point is this is the foundation to anything that you're going to be doing related to multi-threading or multi-process, whatever. That said, it is far from the only way we can make multi-process, multi-threaded programs. This is really just the first step. There are other ways that make this whole thing a lot easier on us, at least for programmers, but really we're going to look at it at the nitty-gritty detail. We're going to look at it at the nitty-gritty detail level because, well, that's how we... Well, it's a good place to start because a lot of things are abstracted away for the programmer's convenience, but we as people who are trying to understand the inner operations of an operating system, we would like to see what some of those nitty-gritty details are like, you know? Okay. Now, super duper important note. And this is in regards to part 1 of your lab. It might not apply to part 2, but I'm gonna say that this applies to both parts. You must do this on a UNIX system. So a Mac will do just fine. A Linux system will also do just fine. You cannot do this on a Windows system because all the system calls on a Windows system are different. So, if you can borrow, for example, a Macintosh computer from someone or the school and do your lab this way, that's good. That'll do. The problem is if all you have is a Windows system. That's it, you still have plenty of options. The first one is to remotely access the school computer labs using, for example, on Windows systems, starting with Windows 10, we now have something called Windows PowerShell, and you can type in, for example, the SSH command. That will let you remotely log into the school computers. However, you need a specific command. You need specific parameters following the SSH, and you also need to download a program called Global Protect. That is a VPN that you must turn on before you can access the school computers remotely. I may just link instructions on how to do that on Canvas. So that's the option number 1. This option number 2 has you create a virtual machine, and then you can install Linux on the virtual machine, and then you can run your labs on that. And that is also a good option. The thing about this is that it's a bit more involved. I will summarize the whole process, but I can't show you the entire install process because it takes some time and it requires one step that I am unable to record. Well, there is a way to record it, but I don't have the hardware for it. Basically, it's this. You must download VirtualBox and install it. You must also download the ISO file for the operating system of your choosing. I am using Linux 64-bit, and if you are using a 64-bit operating system for your virtual machine, there is one extra step that you must also do. And this is the part that I cannot record. It is this. You must restart your computer, and as it is booting, you press F12 or delete to enter the BIOS setting. So there is a specific setting in the BIOS that allows for virtualization, and without this, it's gonna make the virtual machine run like stupidly slow. So hold on. So if you go into your BIOS settings and go into the advanced options, on Intel systems, it's going to be something called virtualization technology. You must turn that on if it's not turned on. If you are on an AMD system, it's gonna go by a slightly different name. Just look for something that says virtualization in the name. You must turn that on, save those settings to the BIOS, and then it will restart your computer, and then we can proceed to the next step. The steps involved with creating a brand new virtual machine involve, well, giving it a name, choosing your choice of virtual machine. For our case, this would be Linux, and then you choose, as I said, I have Ubuntu, so you just choose, in my case, 64-bit Ubuntu, because that's what I have. Oh, by the way, the one really neat thing about this is both the ISO file for Ubuntu and VirtualBox. Those are free to download, but they do take some time to download because they are so big. So be prepared to just sit down and do nothing while your computer is downloading these files. What you also need to do is this. You will need to allocate some of your own computer's memory to what's basically a computer inside your computer. That's what a virtual machine is, in a way. So you would need to download it, just enough memory for it to run, and then you also need to create a virtual hard disk. So this is a big file that, as far as the virtual machine is concerned, is going to think is just a hard drive. You need to create one of those. You have to make it just large enough, something like 10 gigabytes. So yeah, you also need quite a bit of, you need quite a bit of space to make this run. So make sure you have enough hard drive space to store your everything for this. The virtual machine program, the ISO file, and the virtual hard disk. So you're going to need quite a bit of space for this. You're also going to need to, and I'll just show it here. You also need to allocate it a few CPU cores. So if you go to System and go to Processor, you're going to want to allocate it a few of your own system's CPU cores. I cannot change this right now because it's already running. In my machine, I chose 4 CPU cores. So yeah. Once you have that done, there is an extra set of steps of actually installing the operating system onto your virtual hard disk, and then the system would boot from there. I might just also link a tutorial on how you would set up your own virtual machine with whatever operating system of your choosing. Again, I'm using Ubuntu because that's just what I have. But once we have that done, you should be greeted with an interface that looks like this. So, pardon the screen artifacts, it does get a little bit choppy from time to time, even with all the settings that I can affect. But basically, once all is said and done, you should be greeted with a wallpaper that might look like this. And now you can just use it like any other computer. I'm gonna click on Files and go to Documents, and I already have a few folders in here. What I'm just gonna do is open this one, and that's where I already had a few programs already written. And here is our fork and wait files already. What I'm gonna do is this, I'm gonna forgo that and make a new one. Fork and wait again. So for part 1 of your lab, you're simply just making a multi-process hello world program. So there are instructions there is source code in here, but yeah, you are gonna basically copy that, but then you're gonna modify it. So what I'm gonna do is I'll open a terminal, and then I'm going to type in vi fork.c. This creates a brand new source code file. It's a C file. And we could just start typing away. We can start typing, say, excuse me, include UNIX standard.h. However, I'm not gonna use VI. I'm more familiar with a GUI-based text editor, so I'm gonna switch over to that in just a moment. But if you want to use VI, you can. And if you want to save your file, press escape, press colon, and type in WQ. So colon WQ, press enter. That will save your file. And now I'm going to open this in a text editor that I'm more familiar with. So I'm going to double click that, and it's going to open a text editor. And then I can type away. So include UNIX standard.h, include standard io.h, because we don't have access to C in or C out. We're doing this in C, so we don't have a lot of the conveniences that C++ provides for us. Now we need to include a few more things. So include sys/types.h and include sys/weight.h. And now we can start writing out a program. So I'm going to begin with the main function, int main, and there's the body of the program already. It's empty. Let's put stuff in it. So I'm gonna start by creating a new process and save its process ID. So PID, that's process ID. So PID_T, that's a data type that we're gonna use to store our process ID. So PID, and then we're gonna say PID equals fork. Remember, the fork system call returns a process ID. And then we can use that to figure out which process is the parent and which process is the child. So I'm going to continue. If PID is less than 0, then that means something went wrong. So we got to report that as an error. So I'm just going to add some basic handling code for the error. So if PID is less than 0, that means an error happened. Something went wrong. Error happened while forking. P error fork. And return 1. Else if the process ID is 0, if in the program the program reads the process ID and it's a 0, that's the child process. So we can tell the child process to do code that is different from the calling process. So PID equals 0. This means this is a child process. I'm gonna print F hello world from the child process. I'm also gonna print out its process ID. So PID and then %d, and this is just string formatting so we can print out the process ID. So after the end of that line, after the end of that string, I'm also gonna pass in get PID. So this is just another system call that gets the process ID of the calling process. And then I'm gonna say else. If we did not get a process ID less than 0, and we did not get a process ID that is 0, then the only option left is the process is the parent process. So I guess the one weird thing about this is one program that's gonna be running twice. So it's a little bit confusing because, well, at some point we're doing one thing step by step, but at some point we're gonna split into two different directions. So this might be the one confusing thing about all of this. It's the fact that this program, all this code, is going on to two processes, but they're doing different things. They split at some point. And right now we're putting code that deals with that split. So we already have code that the child process does. And now we're going to have code that the parent process does. And what I'm going to do is just cheat a little bit and just do a copy paste. Maneuver hello world from the parent process. And again, I'm going to call get PID to get the process ID. Now, before we do anything else, we gotta wait for the child process to finish. So wait. No. Because if we don't do this, what we're gonna get is improper process execution. If you don't call wait, you might get a situation where resources don't get deallocated properly, or you might have zombie processes or orphan processes. This can happen if we forget to call wait. So let's just wait for, we're gonna have the parent wait for the child process to finish. So wait null, and then after that, once, at this point the parent process is just gonna wait for its child to finish processing, and after that, I'm gonna say printf the child has finished processing, and that's the end of that line. And really, that's the end of the program. So return 0. And I'm gonna save that. So this is the entirety of our program. Don't mind the artifacts on there. Let me just shake that a little bit and hope it disappears. What I'm gonna do now is I'm going to compile this program. So I'm gonna type in a command, and this is gcc. The file name is fork.c, so I'm gonna type in fork.c. I'm gonna expand the window a little bit so you can see the entirety of what I'm typing. So gcc fork.c dash o dash o, and that's a lowercase letter o. And then we're gonna say fork. We're gonna name our executable file fork, press enter, and I got an error. Okay, sys.type.h, no such file or directory. And that's because, well, I made a mistake. It should be types, capital, with an S at the end. So, let's try that again. Fork. And now we do /fork to run a program. So we have now, when this program runs, it's going to be one process that splits into two processes. And then, because we know, we can tell who's doing what based on the process ID, one process can do something, and the other process can do something else. So that's the important thing to know about processes. We can have them do different things. Now, one of the things that you are to do with this program is, well, modify the program to have it say different things. So here in the lab instructions, I have you have one process print out your name and another process print out your favorite TV show. And then you're to take a screenshot of that resulting output. So now we have that in mind. Another thing we can do is call multiple processes. So we're gonna just do something a little bit crude by we're gonna do something a little bit crude by basically having this block of if, else, if, and else copied and then pasted inside of the else. So that way we are calling fork, and then we're gonna call fork again. So here's what that looks like. First, I'm gonna make a whole new file. I'm gonna say vi wait.c escape :wq to save that file, and now I can open this up in a word processor, and I'm just gonna copy paste this first program, and then I'm gonna copy paste all of this and paste it inside of here. So now we have the same block of code, but copy pasted so it's in a nested format. If we want to call even more processes than this, it's at some point you're gonna tire of this copy paste, so you might have to do something such as a for loop to do this. So for now, let's just do it like this, and we're gonna have two process IDs now. So PID1, PID2. So the first process ID is gonna be for the first time we fork. So if we have this PID be less than 0, that means something went wrong, we had an error. If that process ID is 1, we're gonna say this is the child process, and it's gonna say hello from the first child process. And then if that process ID is anything but 0, that is the parent process. We're gonna have the parent process say hello world, but it's not gonna wait for that first child yet. Rather, what we're gonna do is this. We're gonna have the parent process we're gonna have the parent process create another child process. And it's much the same code as before, it's just that it's nested. So if this PID is less than 0, then another error happened while trying to fork. If that PID is 0, remember, if a process is to read this PID value and it's 0, that means it's the child process. So hello world from the second child process. So this is the second child process. And now, if otherwise that PID is anything but 0 and anything but a negative number, that means that is the parent process, and now the parent process has the task of waiting for both children to finish. So we have to call wait twice. I'm going to do a little bit of cleanup here so it matches the format as shown in the instructions, but that is really the base of what we're doing here. So unless I made some mistakes in trying to, well, we'll see whether I made a mistake. So clear. I'm going to clear this, and then I'm going to compile this. I'm going to compile this new program, and I'm going to call it wait. The executable file is going to be called wait, but the source file is wait.c. That should have worked. We'll see whether something bad happened. I'm going to type in /wait, and there we go. So now there's one parent process. It forks and creates a child process. And before the parent process can wait for its first child, it forks a second process. That's going to be its second child. So now the parent waits for 2 processes to finish running, and then it will say it's done. Also note, keep this in mind. In Unix, we can have a hierarchy of processes. So I guess you can start to see that based on the fact that these are consecutive process IDs. So the parent process is in here, PID 11155. The 2 child processes are therefore 11156 and 11157. So yeah, that is the process hierarchy starting to manifest itself. If we kept going and say have one child process make its own child processes, then things start to get interesting, and we'd have like basically a family tree of processes, but we call this a hierarchy. Again, in Windows this doesn't really exist because the parent process has a token that it can use to identify its children, but it can just give that token away to any other process. So that invalidates the entire hierarchy of processes. So yeah, with this program, you are going to modify it so that one process prints your name, one process prints your major, and another process prints the year you're expected to graduate. So that's the instructions I have in here. And beyond that, you're gonna try to run the program multiple times. Though, I think it's better to have it... Okay, so a few things you're gonna do here. Run the program multiple times. Does the order in which the processes print their messages change? Why or why not? Modify one of your programs by adding more fork calls. I should have prefaced this with the following. Whenever you call fork, you must have an accompanying wait. That is just to clean up the... That's just to help clean up after ourselves, okay? I don't want you to accidentally break your system, okay? So, really, when you modify your program so it calls more processes, when you modify your program when it forks more processes, you must have an accompanying wait. So every time you have a fork, you must have a wait. One other thing we can do is we can have it so that the parent process waits for its children in a specific order, and that is what the wait PID system call does. So we were using a different but related system call called wait. Wait PID makes it so that the parent process waits for a specific child identified by process ID. So yeah, that is basically a rundown of this Hello World program using processes. Now, for us to talk about the second part of your lab, we need a rundown of threads. So I'll just give you a sort of preview about that. Now, I'll just go over the main parts of this. Basically, I'll have a video regarding all this material hopefully tomorrow, which is when hopefully I'll have another video regarding this, explaining everything in greater detail. But the long and short of it is this. The POSIX threads library, or pthreads, is a library in which you can make multi-threaded programs. There's like 60 different function calls, but we're gonna deal with only a handful of them. The most important ones you'd have to know are the ones called pthread create, pthread exit, pthread join, and maybe a few other ones after that. So all pthreads have certain properties. It has an identifier, it has a set of registers, and it also has a data structure of attributes. We use these attributes to keep track of the thread's stack size, the scheduling parameters, and anything else that we need to create a thread. So we use pthread create to create a new thread. It's analogous to the fork system call, except there's no accompanying exec call. Once a thread has finished its work, we call pthread exit to terminate that thread. We must also specify which thread to terminate by passing in the thread ID. Sometimes the thread must wait for another thread to finish its work and exit before continuing. This is pthread join, and it's based on something called the fork and join model. This isn't in the book, but you will see it in, for example, parallel programming. A textbook like this talks about what's called the fork and join model, where a process forks into multiple processes, or one main thread forks into multiple threads. that main thread waits for all of its child processes or child threads to finish, and then it joins back with the main thread or the parent process afterwards. The one other thing about threads is this. There is no built-in automatic mechanisms to signal when threads should be switched for other threads, the same way there are mechanisms to signal to the operating system, hey, it's time for this process to run. It's been waiting too long. We need this to run. Give us a CPU, please. So as a programmer, you need to provide the signaling yourself. That is done through pthread yield. That makes it so that a thread gives up the CPU so that another thread can run. So there are also some attributes that we can associate with each thread, and pthread attribute destroy destroys those attributes. There is another hello world program that's not the same. It's a little bit different from the one I have in your lab instructions, but the main point is this. We are... The main point is this. The main thread is going to create a bunch of threads. And then when we create these threads, we're going to pass in a function that tells each thread what to do. And in the rest of these slides, there's a bit more stuff that might be going on behind the scenes, such as, hey, how do we implement threads in the operating system? There's two ways to do that, and they both have their pros and cons. So we're going to talk about that. We're going to look into that a little bit further. And yeah, there is also a third way to do that. And oh yeah. So if you really stuck on what is multi-threading, I can give you an analogy right now, but I will say that I'm just going to repeat it tomorrow. Basically, multi-threading is like the process of building out a Lego train car by car. You can think of the process, the act of building out the Lego train itself, the whole thing. That is a process. Multi-threading is where you have your friends help build out cars one by one. That is what multi-threading is. The point is this. You yourself could probably just build out the Lego train on your own, but if you think about it, if you had an extra set of hands, then building out the train is gonna be way less time consuming, because now you have an extra set of hands who's gonna be creating another train car as you create a train car. And if you have more friends than that, maybe you have like a lot of friends helping you out with building this whole Lego train. You, as the main thread, could coordinate with all of them, and then you can just start building the whole train one car at a time. And I do have other train cars to help illustrate this point. Really, they're just copies of one another. Yeah, all I have is this Lego passenger train. So, yeah, I guess the analogy works better if we were building out a Lego freight train, because there's a lot more variety in train cars that way. But again, I'll talk about I'll talk more about this tomorrow. But I want to get you started with the pthreads part of your lab. So this is part B of your lab. Now you can do this on a Windows system. There is a way to install a Windows implementation of the pthreads library, but for the sake of consistency, I'm just gonna do it all in the same VM as I had before. So we're going to close this, and we're gonna go to a whole nother folder. So as you can tell, I already have it here, but I want to show you the walkthrough of that. So I'm gonna create a new folder, pthreads again. So I'm gonna grab the instructions so we see what we're doing, so we know what they're doing. Now there are a couple of advantages of using threads over processes. Actually, let's go back. You might be thinking to yourself, we're just making multiple things that say different things. What makes them different? And, well, the differences are at a conceptual level, but also might be also down in the hardware. So, one thing is this. With the train analogy, with the Lego train analogy, one process is the act of building out the Lego train. And having multiple threads, that's the act of building one train car at a time, but that's where your friends come in and they're building different train cars, potentially all at the same time. The really important thing to note about processes and threads is this. Context switching is the act of taking out a process from the CPU so that another process can run. It is easier to context switch threads than it is to context switch processes. And that's because if we have multiple threads that are part of the same process, they're going to share a lot of the same resources. So when you context switch a thread, you don't have to context switch out the instructions. You don't have to context switch anything in memory. It's part of the same program. We already have it in memory. So what's the point in unloading and reloading the same thing? Anyway, before I get too carried away with the differences between processes and threads, let's just continue on with this lab here, and I'm going to now create a pthreads source file. So I'm going to call this pthreads.c. So I'm just going to type in vi pthreads.c, press escape, type in :wq. That's going to create my source code file so I can then edit it with my choice of text editor. So we need a few things here. So include standard io.h, include standard lib.h, and include pthread.h. Now we need to make a function that's going to be run on our threads. And that is this. Void star thread function, and then void star arg. And that's our arguments. So I'm gonna add some comments for the purposes of self-documenting code. And now in here, what I'm gonna simply type in is this: printf hello world from thread ID. And oh yeah, this is one slight difference between if you manage to install pthreads on a Windows system. What I'm gonna type in might be different on a Windows system. So this is gonna be %lu. This is gonna be different on a Windows system, and I'm sorry, I cannot recall what it is. If I do figure out what it is, I'll just mention it in the next video. So basically, just as a long unsigned data type. In Windows, it's called something else. So anyway, I'm gonna do !n. So that way, it's gonna say hello world from thread ID. And I'm also gonna pass into this printf pthread self. And this is one of many other pthread functions. This one just returns the ID of whatever thread called it. And then we're going to return null. Now, we can now write the rest of our code. So this is just gonna be the main function. Int main. We're gonna create one thread. We're gonna give that, it's gonna be of data type pthread_t. And we're gonna call this, well, thread. And now we're gonna call pthread create. However, we're gonna put this inside of an if statement. So it's gonna look like this. If pthread create, and we're gonna pass in a few things into this function. The first one is the address of thread. The next thing we're gonna pass in is null. The third thing we're gonna pass in is thread function, because yeah, we're gonna pass in a function as part of our function call. You can do that, by the way. And then we're gonna pass in null again. If this, and when we call pthread create, we're gonna pass in some stuff, but it's also gonna return some stuff. That stuff is going to be something that hopefully is not 0. Because if pthread create returned a value that is a non-zero value, then something wrong happened. And that means we had a problem with trying to create our thread. I'm gonna say p-error pthread create. And then I'm gonna return 1. So now what we're gonna do next is, well, simple. I'm gonna make the main thread call hello world. Okay, so here's what's happening. We end up calling pthread create. So if the thread was successfully created, then now there are 2 execution paths. The first execution path is going to be the main function, but the second one is going to be this thread function. So the thread that we just made, we passed it this thread function, so now it's going to call the thread function. What's happening now is we have 2 threads and they're running 2 different functions. One is the main thread and it's running the main function. The other is the thread and it's calling the thread function. So it means that one thread's gonna do something else from the other thread. So we can continue with our program. The main thread is gonna say hello world, but it's gonna wait for this child thread to finish. And we do that by calling pthread join. So we simply say pthread join thread null. Okay, so that is the entirety of our program. We create a new thread, and if we create a new thread, we're gonna pass in our thread function. If it works, then a second thread is gonna be created, and then it's gonna call the thread function. All the while, the main thread is going to say hello world, while that child thread is also going to say hello world, but it's going to be from calling the thread function. Then the main thread waits for its child to finish, and then the whole program's going to terminate. So I'm going to save all this, and now I'm going to compile this program, but the command to compile it is a little bit different. We're going to start with gcc, and we're going to pass in the file name of pthreads.c. I'm also going to pass in I'm going to also add in dash O pthreads. But there's one more thing I need to pass, and that is dash L pthread. And there we go. That has compiled our pthreads program. The instructions do a terrible job at trying to display it because that should not be a line break. There should be no line break there. So really, it should be this whole string, unbroken, no spaces between the dash or any other characters after it. So it's gcc filename.c dash o file name without the file extension, and then dash lpthread. So there's 5 things you have to type in here. The gcc command, the file name, the dash o, the file name without the file extension, that's going to be the name of our executable, and then dash lpthread. So the process of compiling this is the same except for that 5th thing. So now if I type in /pthreads, there we go. We get hello world from the main thread, but we also get hello world from the child thread. So if we look back at the code here, and it's doing that weird thing again, it's just simply saying hello world from thread ID. Now, one thread is really neat and all, but how neat would it be if we could have as many threads as we want? So I'm gonna copy that, and I'm gonna make a new source code file, and I'm gonna call it pthreads with an extra s. I'm gonna press :WQ, save that, and now I have the same program as before, but I'm gonna make a few changes. What I'm gonna do is this. I'm going to define a constant, and I'm gonna say $define num threads 3. So we've hard-coded a thread count. So now instead of running just one thread, we can run 3. Oh, and we can change that number so we can run as many as we want. So now we're gonna make a few changes to this. So the first thing I'm gonna do is we're gonna do something with these arguments here that we passed in through here. What I'm gonna do is type in int thread num equals star parenthesis int star parenthesis arg. So we're gonna be pulling what we're gonna do is we're gonna pull a thread number. So it's not gonna be the thread number that's returned by pthread itself. Rather, it's a more convenient value that we can use to identify our threads. So it's just gonna be a small number that's it starts scanning it from 0. So we're gonna have a thread 0, thread 1, thread 2, thread 3, and so on. In addition to the main thread, of course. So when we create our it's just like a few weird things I have to do here. So hello world from thread %d. I'm gonna change up this message so it prints out the thread ID as used by the program and the thread ID as given by the system. So we have our thread ID as given by the program, that is thread number. And then we have some other thread identifier that's given by pthread itself. So now we're gonna get to the main program here. So the main function here. So previously we had created a new thread by passing this to the pthread create function. We're gonna do something else here. We're gonna make this an array of pthread t. So now we have an array of threads. We also need a few more things. So int thread args num threads, and then we need int I. You'll see where this is going in a bit. So now what I'm gonna do is I'm gonna take this if statement that we had before. This is what we used to create a new thread. I'm gonna cut that, and I'm gonna make a for loop. For I would say int I equals 0, but I already defined an int I outside, so I'm just going to say for I equals 0. I is less than num threads I plus plus. And now I'm going to paste in that if statement that I had from before. Also, you have to make sure this is all indented properly, but we're not done yet. There's a few more things we have to do. The first thing is we're going to pass in arguments to our thread function. Let me make sure everything's indented properly. So now we're going to pass in arguments into our thread function. So we're going to pass in a more convenient thread identification number. So we're going to say thread args index I equals I plus 1. So really, what we're doing here is, presumably thread 0 would be reserved for the main thread. But here, since we're offsetting everything by 1, we're going to have a thread 1, thread 2, and thread 3, in addition to our main thread. And then we're going to pass this into our pthread create function so that when this is called, it's going to have arguments passed in, and we can do stuff with that. So, for our purposes, we want to change this. So instead of thread, the address of thread, we're going to pass in the address of the element from our thread array. So I'm going to say ampersand thread I. Because we now have an array of thread here, not just one anymore. And for our fourth argument for our pthread create function, I'm going to pass in ampersand thread args I. So that way we're passing in I plus 1 as our arguments for our thread function. We can do stuff with we can pass stuff to our thread function now. There are other ways to do this, by the way. This is just one of them, and this is just for passing a simple thread ID that we can use to, for example, have threads identify one another. So we have a thread 1, thread 2, thread 3. So now, when we call pthread create, there is a chance that at any step of this process of creating threads, any one of them could fail. But assuming none of them failed, then the main thread will simply say hello world again. Now, here's the one other thing we have to do. We're no longer waiting for one thread to finish. We're waiting for multiple threads to finish. So when we call pthread join, we have to do it for each time we've ever called a thread. Since we've created 3 threads, we have to put this in a for loop that calls pthread join 3 times. So I'm gonna put this pthread join in a for loop. So for I equals 0, I is less than num threads I plus plus, and then I'm gonna have this function be repeatedly called for every time you've ever called a thread. I'm gonna print out a final message. Printf all threads have finished, \n, and there we go. That's the end of our program. Now, if you want to compile this thread, it's the same command as before. It's gcc, except you have to add a -lp thread at the end. And okay, now we have a little bit of a problem here that I'm gonna have to go debug. So I'm gonna pause the recording here, and I'll be right back. Okay, I found it. When I say pthread join, it's not just the thread anymore. It's gonna be an array of threads, so I have to pass in thread I instead of just thread. So I'm gonna save that, and I'm gonna recompile it. There we go. It worked. If I type in ls to see what programs we have pthreads and then pthreads with 2 s's. So I'm gonna run that. So ./pthreads, and now there we go. We have a multi-threaded program, and this is really neat because what is stopping us from having a program that does multiple different things? We could, for example, have an if statement in here. And in the lab instructions, there is an example of an if statement that you can copy and use that as a framework for modifying this program. So, by the way, let's go back to those instructions. When you do part 1 of lab 1b, you are going to be modifying the main thread so that it prints out your name. And then the child thread prints out the name of a video game you've recently played. So that's part 1. Part 2 has you modify the program again so that the main thread prints your name, and then each child thread prints out the name of one of your favorite songs. So another thing we can do, now that we have the ability to make new threads, and eventually we could have it so that we are passing in different functions to each thread. For now, we're just passing in one thread, and then we're just differentiating what each thread does by using an if statement. That is one way to have multiple threads do different things. It's just one of many ways we can do this. Eventually, it'd be more elegant if we could just pass in different functions to each thread. For now, what we're gonna do, and what I'm gonna do for the sake of experimentation, is I'm gonna have 30 threads. So now instead of one thread, I'm gonna try to run this with 30 threads and hope that this does not crash the VM. Okay, it compiled just fine. If I run it, okay, there we go. Now we have hello from threads 1, 2, 3, 4, 5, all the way to thread 20. Okay, so that's one thing that you'll encounter. That's one thing that you'll encounter here. And it's this. When we have so many threads trying to compete for the CPU is at the whim of the operating system, and it's the operating system that has an algorithm that ultimately decides which threads to run. And it may be the case that every time you run this, you might have a different ordering of threads each time. So we did 1, 2, 3, 4, 5, 6, 7, 8, 9. But no, 9's all the way down here. So 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 8, and then 30. So so it might be the case that every time you run this, it's gonna have each thread finish at different times. And that is all because of something called the CPU scheduler. We have not gotten to CPU scheduling at all yet, but that is something that we're gonna look into later on. My point is this. Trying to debug a multi-threaded program may be one of the biggest headaches you may ever have. Maybe one of the most frustrating things you'll ever have to do. Though in the case of a Hello World program like this, really the problem is the fact that these threads may not be finishing in the order that you want. But this is a rather innocuous example of threads not finishing in the order that you would expect. This is a problem that has to do with having multiple processes or threads as part of a program. We would need a means of synchronization to make sure that these threads finish in an order that we expect. But let me back up. We need some means of synchronization to make sure that these threads finish in an order that we expect. If we don't have that, and there is a block of shared memory that each thread is accessing, then we have the danger of introducing what's called a race condition. That is where multiple threads are racing against one another to write something into memory before some other thread erases it from existence. And in a race condition, last place wins. I'll talk more about that in the lecture slides, by the way. So yeah, those are some of the things you can do to play around with this multi-threaded program. And remember, it's a rather basic hello world multi-threaded program that you might want to keep in the back of your mind if you are to take parallel programming in the future one day. Or maybe you're taking it right now and you have to learn about this as well. This might very well help out with that. Anyway, when it comes to the deliverables of your lab, basically you're just gonna have the deliverables. The deliverables are simple. You're gonna include the source code files and you're gonna include their screenshots. And then you're gonna include the answers to these 3 questions. If it's the case that you don't see any change in the order at which processes execute, if after you've run it multiple times and you still don't see a change in order, you can report that instead, by the way. What I'm saying is, you might be more likely to see that if you have a lot of things running at once. And particularly in the case of threads. So, run this program multiple times and see whether the order changes. I would go as far to recommend to run this with as many threads your system can deal with. Though, if you're doing this on a public system, be wary about the number of threads you create. You might just suck up all the system's resources. So, maybe don't go too stir crazy with the number of threads. I picked out 30 on my VM because that was a small, convenient number, but really there's nothing stopping me from doing like 300 threads, though I am starting to fear for this VM. I'm gonna try it anyway. If the VM breaks, well, that's the beauty of a VM. If we break it, all we have lost is just some time. And maybe whatever files were on the virtual hard drive. So, clear. I'm gonna recompile this program with even more threads than before for the sake of testing. And it still ran them all just perfectly fine. So why would you want a multi-threaded program? Well, because there are a lot of problems in computer science that have a lot of repeated steps. Insofar that they're basically the same thing, just repeated over and over again. There is one caveat to this. If we have pieces of code that are doing instructions, but here's the point. If we have a program that consists of blocks of code, so block 1, and then block 2, and then block 3, if we find out that we can do those blocks of code in any order, then that has the potential of being done at the same time. This is how we determine what parts of a program can be parallelized. Though, I can say from experience, this is more in the form of for loops, but it also has to be a specific type of for loop. It's a kind of for loop where if you run through it loop iteration by loop iteration, the result of the next iteration is not dependent on the result of the previous iteration. If that is not the case, then we're going to screw up our data computation and we might get the wrong results every time we run it. So, you can only do parallelization for very specific types of workloads where the result of one task or one loop iteration does not affect the result of the next iteration. There are ways to parallelize for loops like this, and my personal favorite is using a library called OpenMP. It basically does all of this, but there are no functions that we call to make threads. Rather, we just write in a few compiler directives, and the compiler does the rest for us. I would love to show you one of those one day. But for now, I think we've covered quite a bit in regards to the lab. So when it comes to your lab, this is basically just part. This is basically a 2-part lab. It might take some time for you to get set up, but that's why I gave it a rather generous 2-week period from the day I assigned it to when it is due, just to give you ample time to make sure you get this all working. And especially if you need to make a VM to do this. So yeah, anyway, that's going to be it from me. I'm going to most likely be providing instructions for if you want to set up your own virtual machine like the one I have here. So that's going to be it from me, and we're going to catch up with the next set of lecture slides. That is going to be all about threads and the beginning of what is called synchronization and race conditions. So yeah, this is about 70-ish slides worth of content, and it conveniently ends on a picture of a bed. I'll explain why that is too. So anyway, that's going to be it from me, and I'll see you in the next video. Take care.